Hello. In this video, I will go over center of mass or center of mass, centroid or center of area, and distributed load. I know we have discussed distributed load before, but in this lecture, it's not only simple distributed load that are either rectangular or triangular, but any general distributed load you should be able to find the intensity and location of the load. So first, let's start with some applications and why should we care about these. A couple of examples here. One is a water tank, and to design the structure, to design the support for this water tank, we need to know, of course, the weight of the tank and the water, but also the location of it and where the resultant forces are applied are as important. In design of sport utility vehicles, the center of mass is really an important aspect in designing. The height of it and location of it is an important aspect in design of SUVs. Here are a couple of more examples. Again, one is finding the center of gravity or center of weight for this football goal post is important, and we're going to learn how to use integration to find the center of weight of this, or center of area, or center of mass. Here's another example that I have: a snow on the roof of a cabin or a shed or a house. These are good examples of distributed load, and as you can see, it's not a simple area anymore that we can just find the area or centroid of it. So we need to use integration to find these loadings. To start off, I'm going to start with center of weight, center of gravity, and we're going to start with a wire. So we're just assuming that this is a one-dimensional, okay? So it only has x direction. So I'm going to take a differential amount of weight, and the total summation of all those weight is W, and is applied at G, or center of gravity. Okay, this wire is considered like a rigid body. It consists of infinite number of particles. So weight of each particle is that differential amount of dW. Okay, so total weight, which is W, is summation of all dWs. Okay, we cannot use sigma anymore for summation, because sigma is for finite number, something that we can count, 10, 20, 50. But here, all of these dWs, we cannot count them. So instead, we're going to use integration. So summation is that. Okay. Now let's look at the moment. Well, before that, let me explain what those x bar and x tilde is. So x bar is location, or the distance of G to y-axis, or center of gravity to y-axis. And right away, I want you to pay attention to something. It's x bar, it's distance to y. Okay, so they're always opposite. And then the x with a squiggly thing on top, which we call it x tilde, is distance of dW to y-axis. So the distance of that little differential weight to y-axis is x tilde, and the center of gravity, the total weight location to y, is x bar. Okay, now let's use the resultant moment about y, which is the summation of moments about y. Okay, I'm just using sigma as a symbol here, symbol of summation. Moment of w about y is w multiplied by distance to y-axis, or in other words, w x bar. The other side is sum of moments of weights of all particles. Okay, or moments of all of those little dw's. And that is going to be particles about y. And this is going to be x tilde dw's. Okay, so now these two needs to be equal with each other, and therefore the x bar, center of weight, what I'm after here is going to be x tilde dw over dw, integration of dw. And remember, this dw was total weight, so it's the same thing as this. Okay, so this was one dimension, meaning only x. If I repeat the same process for an area, so now this is an x and y, I have again the differential amount of weight located at x tilde. Remember, they're opposite. X tilde, distance to axis y, y tilde, distance to axis x, x bar, centroid, center of gravity, center of gravity to y-axis, y bar, center of gravity to x-axis. If I repeat the same procedure that I just did, I'm going to have, let me just write this from previous slide. Now I'm going to have y bar, y tilde dw, integral of dw. Now if I have a 3D body, that potato that we've had before, so all I'm doing is adding a z-axis to it. So again, I have x tilde, y tilde, z tilde. I have y bar, x bar, z bar. If I repeat the same procedure, I will add a third dimension to what I have. Z bar, z tilde, dw over integral of dw. Now let's look at the center of mass. Okay, so we talked about that SUV and how important it is to know the center of mass for it. It is essential to know center of mass to find a dynamic response or acceleration when it comes to motion of a body and its stability that we care about. So the location of center of mass, that's why it's important. So I want you to remember this. This was for center of weight. Now if I write differential amount of weight, do you agree that I can write it as dm, differential amount of mass, multiplied by g? acceleration due to gravity. So all I have to do is, in the other integration that I had, replace dw by g dm. G dm. G is a constant, and it gets taken out of the integral and then cancels out. So what I've left is x bar integration of x tilde dm integration of dm. Y bar y tilde dm integration of dm. Z bar z tilde dm integration of dm. Now think about it. If the rigid body is homogeneous, what does that mean? That means rho is constant all through. The density is constant. So then I can write, take this dm. dm is going to be rho dv, which is d volume. Okay, so volume, density, mass, or differential amount of mass, density, differential amount of volume, and replace it here. Now what I have is x bar x tilde dv integral of dv, y bar y tilde dv integral of dv, z bar integral of z tilde dv over integral of dv. So location of center of mass to y-axis, location of center of volume to y-axis, to x-axis, to xy plane, and so on. X-axis to x-axis to xy plane. So you kind of see a trend here. Let's see. Center of weight, what I have here is differential amount of weight. Everything else is the same. Center of mass, differential amount of mass in the integral. Center of volume, differential amount of volume. Now I want you to think about it and tell me what a center of area would be. So it's the shaded area, which is, what it means is area bounded by the curve of y, some sort of function, some sort of equation of fx and x, y axis. So if you want to look back and find a common trend here, x bar centroid, so distance centroid to which axis? To y-axis. Remember they're opposite. Equals integral of x tilde dA over dA. Y bar centroid measured from x-axis, y tilde dA integral of dA. One thing I want you to remember, okay, about integration, I have dA, so my integral is an area integral, which I'm not writing it here, but it's an integral over an area. Remember that, okay? Last thing I want to mention is we usually show centroid by dot C, and center of weight, I don't know if I have it or not. Usually, yes, I do. usually is shown by G. So everywhere that you see G, that means center of gravity, center of weight, and everywhere that you see C is usually center of area or centroid. Okay, I'm going to do examples of what does that mean and how to do the integration, but here is a little start to the procedure. So x bar, x tilde, dA, and dA, and same thing with y bar, y tilde dA, integral of dA. Again, remember these are area integral. So to find x bar, we need two things. We need x tilde, we need the differential amount of area. X tilde is the distance between centroid of dA and which axis? It's always opposite, y-axis. And dA is the area of I should have said differential area of a differential or element representative. Okay, other words, differential amount of area. Okay, so if we can find these two for any area, then we can just integrate them and find x bar and y bar. So I have two examples here. For the same area that we discussed, we have drawn a shaded area of element or differential amount of area. So for this one, I need to find x tilde and dA. So let's see, x tilde is the distance between centroid and y-axis. So it's right there. And this area can be anywhere from 0 to this x, I don't know, let's call it x2, this point. But at any given time, for any arbitrary element that I draw, this x tilde is always the distance between center of this rectangle and y-axis. So in this case, it's x. dA, so this area that I drew, or differential amount of area, it's a differential amount of width, it's dx, and the length of y. At any given time, it is on this curve which has the y value. So dx multiplied by y. And let's see, for y bar, I need y tilde, which is distance between centroid of differential amount of area and x-axis. In this case, the centroid of that rectangle is in the center of it. The distance between that center and x-axis is y over 2. And d area is not changed, it's the same way. Let me write y this way. It's a little bit easier. Okay, so now I can put these back in those two integral and then start integration. If I have a horizontal strip or differential amount of area, I'm going to do the same thing. X tilde, distance between centroid of dA and y-axis. Centroid of dA and y-axis is right there. If this length, entire length is x, center of it is halfway, so it's x over 2. Let's find y tilde. Distance between centroid of dA and x-axis at any given time, that located at y, dA has differential amount of width of dy, and the length at any given time is x. Same thing for y. I'm going to write it this way, x dy. So for a problem like this, the procedure is to first decide which element we want to use, and I'm going to give you some tips later how to pick this element so your life is much easier and it requires less calculation. But you can pick any of them and then start integrating based on these formulation. All you have to do is find x tilde or y tilde and the differential amount of area. So if you look at the back of your textbook or open any other engineering textbook or engineering design book or engineering handbooks, you're going to see tables like this. So for a lot of common shapes, they've already calculated in some common forms of function that you see, they've already calculated the x bar and y bar and the total area for you to use. But let's see how you can use that. You're going to use that in something called a composite area. Composite area is something that consists of a series of connected, let's call it a simpler shaped areas. Okay, so simpler means something that we probably already know the centroid, or we can find it in one of these tables. So if you can break down this area that we have, this shaded area, blue area that we have, then it's much easier. You can skip the integration. And we're breaking it down, so we're going to have finite number of areas. Okay, so we can change the integration into summation. So for a case like this, x bar is summation of x tilde w's summation of w. Well, let's not use w. Let's use, because I'm thinking about area. For a second I was thinking about weight, which there's nothing wrong with it, but there we go. Okay, so this is centroid of each area of each area. Okay, and this whole thing would be the total area, and therefore this would be centroid of the entire area, the composite body. I can say the same thing for y bar, summation of y tilde dA's, oh sorry, there's no d anymore, a, because remember these are simpler areas that we can figure out. How did it get black? There we go. Summation of areas. Okay, and I'm going to explain like how can we break this down. What do I mean by simpler? Look, this area, you got to think how this area was generated. Okay, and it's like an algebra equation. You can put them next to each other and figure it out. So they started probably with a square right there, then they added a triangle, then they added a half circle. Okay, up to this point what we have is, let me draw it here, I need the area below. So was a rectangle, they added a triangle, They added a half circle. This is what they have so far. So 3 areas, 3 simple areas. And then they decided to deduct a circle from it. So it's not always addition, it could be subtraction. They deducted a circle from it. So minus a circle from there, then they got the shape that we see there. So it could be subtraction or addition of area. Any way that you can construct this. Okay, here's another way that you can construct it. They can have a bigger triangle, or sorry, rectangle, add half circle to it, then deduct a circle from it, then deduct a triangle like that from the bottom of it to get to this shape. See? So they deducted this triangle and they deducted the circle. So any way that you can construct this area, you are welcome to do that. Once you do that, for each area, so it has a rectangles 1, 2, 3, 4. So 1, 2, 3, 4. Remember, let's look at the equation really quick. Centroid of each area, area of each area, sounds kind of funny. Centroid of each area, area of each area. So I got to find centroid of each area and area of each area. Look, centroid of each area, area of each of those area, and hopefully they're simple enough that you can figure it out. And then once you do that, you put it in this equation. So all of the x bar multiplied by area, all of these multiplied by these, they've been added together. And all of the areas also added together here. So these were added here. We have them right down below. And this will result in x bar. This x bar, remember, it is the distance between centroid of this shape and y axis. So I'll draw it later. Same thing with y. Y multiplied by each of these area, which they have it back here. Summation of all areas and y bar each area. So they use y bar. In my equation, I use y tilde to just be a little bit different. Okay, but they use capital letter X, small letter x bar to be distinguishable for you guys. So, and you find y bar of total area. X bar, distance to y axis, remember. So distance to y is 54. 120, so this center is at 60, so a little bit less than 60. Okay, this distance here, 54 something, 55. Y bar is the distance to x axis. It's at 30, let's call it 37. Distance to x axis, 37. 80, half of it would be 40, a little bit less than half of this. And this is y bar, 37. So the center of this area is located right there. The distance to y-axis, the distance to y, and where those two intersect with each other. I'm going to do a lot more examples on these, and they get easier as you do more examples. So make sure to watch next video. Next video, I'm going to do these examples. At least these examples. I might add a couple more to them. But going back, I just want to mention, going back to distributed load that we had. Remember, if you want to replace a distributed load by its equivalent for a problem like this, so you have to find F1, and remember, we put it at x bar. Before it was just a simple distributed load, you could just find the intensity. So the intensity was area under loading. In this case, you have to do integration. And the distance is centroid of the area, which we got to use that equation, x tilde dA dA integral of area. Same thing with this, with the one on the right side. So that's why once you know how to find centroid, then you can do any distributed load equation, get rid of the distributed load, and put it as a single concentrated force. Thank you.